Well, hello there again. It is Chemistry A, Unit 3, Quantum Mechanics, Intro to Bonding, and our final day of notes. So let's get started. Okay, now every so often a bond will take place between elements where one element shares both bonding electrons. This is called a coordinate covalent bond. Okay, so every once in a while you'll get an element that, look, I've got an extra one, I'll share two of mine instead of just one, and we'll make this work. And this is a coordinate covalent bond, and the most popular type of coordinate covalent bond is a polyatomic ion. Okay? Polyatomic ions are tightly bound groups of atoms that has a positive or a negative charge, and it behaves as a unit. Please draw in the box ammonium at the bottom of page 223. So as you can see, the hydrogen has bonded to the nitrogen, and there are 4 hydrogens that bond to nitrogen, which only has 5 valence electrons. So what happens is we get this polyatomic ion. It is a positively charged or negatively charged atom, and it behaves, or ion, and it behaves as a unit. In this case, the overall charge is positive because there is one electron that is not around. Okay? Now, switching gears a little bit here, we're going to talk about bond dissociation energy. All right, this is the energy that is required to break the bonds of 2 covalently bonded atoms. Okay? So the energy that is required to break away the bonds of 2 covalently bonded atoms is called bond dissociation energy. Okay? If the bond is extremely strong, it will take a lot of energy to break that bond. So therefore, there will be large bond dissociation energy. So the stronger the bond, the larger the bond energy, dissociation energy, or the energy that is required to break the bond. Okay? Now there's something else about covalent bonds, and that's something called bond polarity. Now remember, covalent bonds involve electron sharing taking place between these 2 atoms, or more atoms, 2 or more atoms. Okay? The bonding pairs of electrons in covalent bonds are pulled between the nuclei of the atoms sharing the electrons. Now, if the atoms in the bond pull equally, the bonding electrons are shared equally, and the bond is non-polar covalent. So, we have element X and element Y, and if they are bonded together and each nuclei are pulling on the electrons equally, in other words, there's a little bit of a tug of war, not like ionic bonding, but a little bit of a tug of war between this nuclei and this nuclei. And if they pull those equally, or very, very close to equally, then the bond is considered nonpolar. Okay? Molecules that are made from identical atoms, in other words, example, a hydrogen bonded with another hydrogen, will be nonpolar because each will pull with the same amount. That should make some sense to you. You have 2 bond atoms that are bonded together that are identical, meaning they have the same electronegativity as the other one, therefore they have the same strength, therefore there's not one that can pull farther or harder than the other. Now, if the atoms in the bond will pull unequally, the bonding electrons are shared unequally, the bond is called polar covalent. What that means is if this atom over here in my left hand is stronger than the atom in my right hand, then this atom on the left will pull slightly the electrons closer to it than the other atom. Now they're still sharing them. It's just that these electrons are a little bit closer to the other atom. And if that is the case, we call that a polar covalent bond. The more electronegative atom attracts electrons more strongly and gains a slightly negative charge than the less electronegative atom, which then gains a slightly positive charge. So we have 2 atoms. So here we have 2 atoms, and we have a highly electronegative atom on this side, and a less than electronegative atom on this side. and in the middle is the bond. Now the bond is being shown here by the 1 dash, okay? But imagine that the electrons are flying around in here, and they're a little bit closer to the black atom on this side because of the highly electronegative charge, all right? So this one has the negative electrons closer to it most of the time, so it obtains a slightly negative charge. And this one has the electrons around it slightly less amount of time, so it is slightly positive because of the fact that the electrons are on the other side. Now, if this atom were two equal ones, so let's assume for our purposes that black and black meant the same thing, they would be in the inside, they would be right in the middle, and there would be no bond polarity at all because they are equal. Now, the higher the electronegativity value, the greater the ability of an atom to attract the electrons. Okay? We can look at two atoms and figure out their electronegativity, and we can determine how they are going to bond based on the difference between the two electronegativity charges of those atoms. Okay? Now, remember, the presence of a polar bond in a molecule often makes the entire molecule polar. In a polar molecule, one end of the molecule is slightly negative and the other end is slightly positive. Molecules with two poles are called dipole. All right? Now, there are also attractions between molecules. Molecules can attract each other by a variety of forces. Intermolecular attractions are weaker than ionic or covalent bonds. Okay, so what we're saying here, folks, is that a molecule, something like this, can be attracted to another molecule. All right, and that's this intermolecular attractions. Those attractions are weaker than either the ionic or covalent bonds that make them up themselves. Okay. Now, there are types of attractions, and one of those types of attractions is called van der Waals. These are the two weakest attractions between molecules. So the van der Waal forces are the two weakest attractions between molecules. Number one, or letter A, is the dipole interactions. This is a type of van der Waals, don't forget that. They occur when polar molecules are attracted. Electrical attraction involved occurs between the oppositely charged regions of polar molecules. Please, in the box below, draw figure 8.25 on page 240. The dipole interactions are shown by the dashed lines between the molecules as opposed to solid dashes as you see in with the bonds. The second type of van der Waal force is called a dispersion force. This is the weakest of all molecular interactions. Okay? Dispersion forces are caused by motions of electrons. An electron momentarily more on one side of a molecule closest to a neighboring molecule, their electric forces influence the neighboring molecule slightly. Okay? This causes an attraction between the two molecules similar to, but weaker than, the forces between permanent polar molecules. All right? Hydrogen bonds are another attractive force in which a hydrogen covalently bonded to an electronegative atom is also weakly bonded to an unshared pair of another. Can be in the same molecule or in a neighboring molecule. So take a look at the diagram here on the page. You will see a hydrogen bond. This right here, the dashes represent the attraction between the in the hydrogen bond. What we have here is oxygen, which is attracted to the hydrogen because of the opposite poles. Okay? And this bond here is the reason we have water. All right? It is a weaker bond, all right, but it is still a strong enough bond to hold water together. The key point is to remember, if you are going to form a hydrogen bond, or a H bond as I've got here, a covalent bond must already exist between a H atom and a highly electronegative atom, such as oxygen, nitrogen, or fluorine. Let's go back for just a second, and you can see that rule is followed there because we have that oxygen is one of those highly electronegative atoms that is attracted to the hydrogen. Okay? The hydrogen bond is the strongest of the intermolecular forces, but remember it is still weaker than an ionic or covalent bond. And hydrogen bonds are extremely important in determining the properties of water and biological molecules like protein. Okay, at this point it'd be a good time to take a quick summary of the characteristics of ionic and covalent compounds. And you can see those here in this chart. And here you go. Go ahead and write that down. And that is the end of our unit.